In this example problem, we're going to do another chi-square hypothesis test, and this time we're going to do it for something that this type of statistical analysis really excels at, and that's determining if there is dependence between your two different variables. In this example, we're doing a study, and researchers are trying to figure out, is there some type of association between food insecurity, people not having enough food in their house to meet their nutritional needs, and academic performance? So if there is a dependence between these two different things, students, we're going to assume that are food insecure are less likely to be successful in the classroom, while kids that do not have to worry about food security are going to have stronger academic performance. There's going to be a relationship between these two variables. So these researchers went and they surveyed community college students from a large divergent socio-demographic area, and they determined, based upon the results of their interviews in this case, what was the students' food security level and what was their accompanying final grade. So we've got a bunch of information over here. We've got one, two, three, four, five, six intersections. We have the number of students that said that they were food secure and ended up with a C average, food secure and ended up with a B average, and food secure that ended up with an A average. And then underneath, we have the amount of students that said that they were food insecure that ended up with a C, B, and A average, respectively. Just like we always do for a chi-square test, once we have our data formatted in a proper table, which we do right now, we find the total for all our rows, columns, and the grand total for the study. So what amount of students in total identified as food secure? My computer is not liking me right now. 12 that had a C, 55 that had a B, and 42 that had an A. It's a total of 109 students. We can do the same thing for food insecure. 25 got a C, 60 got a B, 27 got an A. That's a total of 112 students. For students that got a C, we had 12 students that were food secure that got a C and 25 students that were food insecure that got a C. That's a total of 37. And we can just keep adding up our columns. We had 55 and 60 for Bs. That's 115 total Bs. And we had 42 A's from students that were food secure and another 27 from students that were food insecure for a total of 69 A's across all of our students. And then for our grand total, you can sum up either the column totals or row totals. It doesn't matter which way you go. I'll go across my column totals, and that comes up to 221 students we must have surveyed. Well, now we have to figure out, based upon the portion of our 221 students that ended up in our six different possible combinations, what percentage would we have expected over here? So we need to find our expected count for all six intersections of our two different variables. And we do that now a little more complicated than we did in previous example because we've got more things going on by finding the product of our row total and our column total for that intersection and then dividing it by our grand total. So for the expected count of food secure students that ended up with a C average, we're going to start with our row total, and our row, they were food secure students, so that row has a total of 109 times the column total, and the columns are our letter grades. These are for students with a C average, so the total number of C's, that column has a total of 37. Then we divide it by our grand total, which was 221. And based upon that, we would expect out of a study of 221 students that we would get 18.25 students that got a C average who said that they are food secure. And I'm just going to repeat this entire process 5 more times to figure out my expected count for all of our different intersections. So for food secure students with a B average, 109 is still the row total. The column total, now we're on to B, is 115, and we divide by the total size of the study, which is 221, we come up with 56.72. For food secure students with an A average, 109 is still the row total. Our column total for A is now 69, multiply by that 69, and then divide by the total size, the grand total of 221, we come up with 34.03. Moving on to our food insecure students, the expected count of food insecure students with a C average. Now the row total is the total amount of food insecure students, which is 112. We multiply that by the column total, 37 total Cs we gave out, and divide by the 221 student total sample size of the study, we get 18.75. Food insecure students with a B average, row total of 112, times the 115 column total divided by 221 food insecure students is 58.25. And for our last group, which is the expected count of food insecure students with an A average, we take the row total, 112 food insecure students, multiply it by the column total, 69 total students that got an A, and divide by 221. We come up with 34.97. So now we have our expected amounts for each of our 6 possible combinations. Well, let's find our chi-square statistic using the formula that we have used previously. And we're going to start with our food secure students that had a C average. So this is going to be equal to the observed amount of students that were food secure. They got a C average, which we have up here as 12, minus the expected amount of food secure students with a C average, which was 18.25. Close that parenthesis. We're going to square it. And then we're going to divide by that expected amount of 18.25. We come up with 2.14. For food secure students with a B average is equal to, in parentheses, the observed amount of students that had that intersection. There was 55 food secure students that had a B average, minus our expected amount of food secure students, which was 56.72. Close that parenthesis, square it, and then divide by the expected amount of 56.72. We come up with 0.05. For food secure students with an A average equals, open a parenthesis, the observed amount in our study was 42 students that were in that intersection, minus our expected count, which was 34.03, so way more than we, 34.03, way more than we expected. Square that difference and divide by the expected amount, 34.03, and we get 1.87. For food insecure students with a C average component, this is equal to, open a parenthesis, the amount of observed food insecure students with a C average was 25, minus our expected amount, and we expected 18.75 students to be food insecure to end up with a C average. Close that parenthesis, square it, and divide it by that expected amount one more time. So the formula's looking a little something like that. Go with 2.08 equals, for our next intersection of food insecure students with a B average, the observed amount. We had 60 students that were in that intersection, minus our expected count of 58.28. Close your parenthesis, square it, and divide by the expected amount. And you get 0.05 again. And then for our last intersection, it's equal to the observed amount of food insecure students that ended up with an A, which we have as 27, minus our expected count, which was 34.97. Square that. Ooh, put a ampersand in there. Hold on one second. There we go. Square that. And divide by our expected amount of 34.97. You get 1.82. So now to find the chi-square statistic for the entire study, you just find the sum of the components. So equals the sum of those 6 numbers, and it comes out to 8.01. So now that we have our test statistic in here, we can perform our hypothesis test. And I'm not even going to bother putting it in numbers right here. Your null hypothesis is, in this case, if you're testing for independence, that there is no relationship between the two, that they're independent on it, which would imply in this case that food security has 0 effect on a student's academic performance. And your alternate hypothesis, always when you're testing for dependency or association between the two, is that there is relationship, that there is association, that food security, in this case, has an effect on a student's grades. So let's convert that chi-square statistic to a probability. And this should be the probability. There we go. To do so, I'm going to use the chi-square.distribution.rightTail function. So CHISQ.dist.RT, open a parenthesis. Our statistic was 8.01. Now I got to determine my degrees of freedom. And it's given in the problem as 2. So how do I know that it's 2? Because for chi-square distribution, What you do is you take your two different variables and how many potential outcomes that you could have. So for our grades, there was one, two, three outcomes, and for our security level, there was two possible outcomes. What you're going to do for each one of those is take the amount of possible outcomes and subtract one. So we have one, two, three here. That is three minus one, two. Over here we had one, two. Two minus one is one. And then after you have your n minus one, if you will, for both of your variables, you just multiply them together. So three minus one is two. Two minus one is one. Two times one is how I arrived at degrees of freedom of two. So I throw that in and I come up with a probability of 0.018, which implies in this case that if we state that the alternate hypothesis is true, that food security and grades are dependent upon one another, we have but a 1.8% chance of that being wrong once we get to a bigger sample size than the 221 that we have right here. Our significant evidence level of 5% means that we're going to give ourselves a 5% chance of making a type 1 error, of making the claim that the alternate hypothesis is true and being wrong in the long run. Well, 5% is the amount that we're willing to accept. Our probability, according to our test, is only 1.8%. So our P is less than our alpha. In any hypothesis test, doesn't matter if you're using X, T, Z, any different kind that you could have, whenever your P, your probability, is less than your alpha, your significance level, you reject the null hypothesis in favor of the alternate hypothesis because you have significant evidence that the alternate hypothesis is true, in this case, that food security and grades are dependent upon one another.